dudes, Dude the Builder here, and in this episode of Zig and Def, we're going to be talking about type coercion and casting in Zig. And this refers to a situation when you have a value that has one type, and it has to be used in a context that requires another type. Basically, one of two things are going to have to happen. Either the type can be coerced, or it's a type of automatic conversion to the other type, so it can be used in that context. Or you have to do an explicit cast, which is a conversion performed via a built-in function. And whether it will happen as a type coercion automatically or as a cast that you have to do explicitly depends on the situation, and that's what we're going to see in this episode. First of all, we're going to cover the instances of type coercion, and I would call the type coercion in Zig a smart implementation of type coercion compared to other statically typed languages, because there are other languages that pretty much don't allow any type of type coercion. You have to always do explicit casts, because there has been a history of dynamic languages that try to implement a clever type of type coercion, which causes surprises in your code, things that are unexpected at runtime because of those types of conversions between types. So many languages, statically typed languages with strict typing, have taken the extreme approach that there is practically no type coercion at all. But Zig takes an approach that it will allow type coercion if it's safe and unambiguous, as we will be seeing here. One of these situations, it's what's known as int widening or float widening, which basically is the situation where you have an integer or float of one type that needs to be used where an integer or float of another type is expected, and that original type is smaller than the target type. So the target type can represent all of the values of the original type safely. No data loss will ever happen. So in that case, Zig will allow this type of type coercion, and that's what we have here. We have a series of assignments here, or declarations with assignments. And we start out with a U8, and we can assign that U8 to a U16, we can assign that U16 to a U32, and so on with the 64 and 128-bit versions of the integers, okay? And the same thing applies for the floating point numbers. We have an F16 here, we can assign it to an F32, F64, F80, F128, okay? And this is allowed because in each of these cases, the next target type can represent all of the values of the previous target, the previous original type, okay? So, and as I mentioned in these comments here and here, there's also an additional type coercion being demonstrated here, and it's the type coercion of numeric literals in Zig. An integer numeric literal like this one, 42, has type comptime int in Zig, and we're assigning it here to a U8. So basically, a comptime int will be coerced to another integer type if, once again, its value can be represented by that target type, which is the case here of the U8, okay? And the same thing goes for a literal floating point number, which would be a comptime float. And you can assign it to a concrete floating point type if that type can represent its value safely, okay? Another place where type coercion can happen is when we're calling a function, and that function requires certain types for its parameters and for its return value. If we go back here to the top, we have a function here called add, which takes U8 a U16 and returns a U32, and it just adds its two parameters. Okay, so if we take a look here, when we call the function, we are declaring here a U8, and we are calling the function with that U8 for both arguments, okay, of the function call. So in the case of the second argument, this U8 is going to be coerced into a U16, okay? And when we see the result, we're going to see that the result in effect is going to be a U32, because that's the return value type of that function, and that type coercion also happens without any issues, because the U32 is bigger than the U8 or the U16. So let's take a look at that output here briefly. And it's here the function, as you can see, the result is 84, and it's of type U32. A situation that may be dangerous is the reverse of widening, which would be narrowing. In that case, you have a type that's larger, and you're going towards a target type that's smaller. But the type coercion in Zig is smart enough. If you have a comp time known value, like here, the value of this BU64 constant is 2000, okay? And 2000 is a value that can be represented in a U16. And that's what we're doing here. This U64 would be coerced into a U16 when we make this function call. And as we see here in the output, in comp time narrowing here, this example here, we successfully get the correct result, and it's a U32, okay? So that type of coercion is also allowed. But if we have a situation where the value is too big, let's say that it's 20 million, okay? Save this, it's comp time known, let's clear the screen, try to run this again. And now we get a compile error, okay? Because at compile time, Zig can detect that the type, as it says here, U16 cannot represent the value 20 million, okay? So if it's comp time known, then we will have a safe coercion if it's possible, and a compile time error if it's not. Now we're going to see that type coercion can also happen between the different types of pointers in Zig. As we saw in the episode talking about pointers, there are a few types of pointers in Zig. And if it's safe to coerce between those types, then the coercion will happen. Here we have an array, and here we basically are creating a pointer to an array here with the address of operator, and the target type in this declaration and assignment is a slice of const U8, okay? And since we have an array here of U8, we're creating a pointer to that array. It can be coerced into a slice of const U8. And also, that same pointer to an array can be coerced to a multi-pointer to a const U8, okay? So these two types of coercions from a pointer to an array, they are safe, so they can take place, okay? We can also have type coercion from types that are allowed in an optional type, okay? So an optional U8 can be either null or a U8. So here, the value null will be coerced to this type optional U8. And here, the value a U8, which is a U8, will be coerced to optional U8 also, okay? The same applies for error unions. This type is any error or a U8. And we are assigning here an error, which will be coerced to this type, to this error union type. And here we're assigning a U8, which will be coerced to that error union type without any problem. Okay. Now we're going to take a look at what I mentioned briefly about a type coercion that's called peer type resolution. And this is the case when we have certain operations in Zig that may produce different values of different types. And what Zig is going to do, it's going to determine if there is a common type that can be safely the coercion target of any of the types involved. And if so, it will then coerce the type to that resulting type. So here, that's why I'm calling this variable happy medium, because we are either returning A, which is a U8, or F, which is an F16, okay? So we're going to see in the output that the type that can be successfully a coercion target for these two types would be F16, okay? Because we can safely coerce a U8 to an F16. All the values can be represented without data loss. So let's take a look at the output once again. And here where it says peer if, we have it's either a U8 or an F16. Well, the result is going to be F16. We have the final result is 3.14, and it is indeed an F16. Okay, so that's an example. Basically, that whenever you have any type of construct in Zig that can return different values depending on conditions, for example, the if or the switch, or when you use a for as an expression, or when you use a while as an expression. In all of those situations, you have like different branches that can return different values. Well, those values have to be either the same or they have to be able to be coerced to one common type, okay? Peer type resolution also happens in certain operations, binary operations, like in addition, okay? So here we are adding A plus E, and E is a U128, A is a U8. So the resulting type will be 128, okay? As we can see here in where it says peer add, the resulting type is U128, okay? Because that would be the safe coercion target type. Now we see when we can't have a safe coercion, then we have to do an explicit cast, okay? And here we're declaring a new constant called K. It's going to be of type U8, and we're trying to assign it the value of F, which is a floating point, an F16, okay? If we take away this cast, let's remove this, and we try to run this program, we see that we get a compile error. It's telling us that the fractional component prevents the float from coercing to type U8, okay? There's going to be some data loss there. So Zig won't do that automatic coercion because it's not safe. So if then we do an explicit cast, and casting in Zig will always involve the use of built-ins, okay? And we have this built-in called int from float, which will turn this floating point F16 into an integer, and int from float will determine what the target type is from the context, which in this case we're saying that K is going to be a U8, so it'll convert to a U8, okay? Now we're going to see the other way around, going from casting from an integer to a float. In this case, the cast is really not necessary because we can coerce the U32 to an F16. In this case, the value is comtime known, and it can be represented in the F16 without any loss, okay? But I'm showing here the use of this built-in, so you can see how you would do an explicit cast. There's also a built-in for casting among pointers. Here I'm using pointer cast, and B slice is just a normal slice to constitute, and we are casting it to a multi-pointer of constitute. This has to be done with a pointer cast because the slice, as you may remember, has the length information, and when we're casting it to a multi-pointer which doesn't have any length information, that information is going to be lost. Okay, so you can't do that type of coercion automatically. You have to go through an explicit cast, and you can do that with the pointer cast built in. Okay. Next up, we're going to see an example of how you can reinterpret the bits that comprise a value without changing that value, without changing those bits. Okay, when you do a cast, like for example here, float from int or int from float, you are actually changing the representation of the value to something else, because the representation in memory, the actual bits that compose a value, will change depending whether it's a floating point number or an integer. Now, when we use the built-in bit cast that we are going to see here, that will change basically the type of a value, or more specifically the type of the bits in memory, but it will not change the bits themselves. Okay, so it's basically like we can change the type without changing the representation. Here we declared this f64 3.14.1592. We do a bit cast of that floating point number, and the target type is U64. Okay, so this bit cast will change the type to U64, but it will not change the bits. Then we use an explicit cast, okay, in this other variable as U64, and we convert using an explicit cast int from float to U64. We also here go back, basically we also do a bit cast of the bits, which is this U64, to go back to the F64 type, and we save that in the as F64. So we basically take an original F64, convert it here to a U64 without changing the bits, and then here we go back without changing the bits with a bit cast back to F64, and we should have the resulting value should be exactly the same as when we started. Okay, and that's what we're going to see in these different print statements. So if we go here to the output where it says bit cast, we see when we started out with the F64, okay, here we have, after doing the bit cast, it's a U64, but the bits are from the original F64. Okay, these bits would be the representation of that floating point number in memory. Now, when we do convert to a U64 using a cast, we see that the value changes and the bits change. Now we only have 1 1 because 3 in binary is just 1 1, 11. Okay, and when we convert back these bits from U64 to F64, we see that the resulting value is exactly the same as the original. Okay, and finally we're going to see a little built-in that can be a bit drastic but there may be situations where you need this type of operation, and we're first demonstrating here using an int cast, okay, from that U64 to the U32. And when you see here in the output, you see that we get here without any problems, because it can be represented in the U32. But if we increase this to 20 billion, and we try this again, now we get a runtime panic, okay? And the panic is telling us that integer cast truncated bits, okay? So the two important details about this is that the int cast, when it results in an operation that loses data, will result in a runtime panic. And you can't do this type of casting if there's going to be data loss, okay? Now, if for some reason you can handle the loss of the data, then you can use the truncate built-in. Let's run this again. And now we don't get any error, and the resulting value is this number right here, which isn't 20 billion. It's basically what's left over, that representation of the leftover bits after we do the truncation. We're basically chopping off 32 bits and leaving 32 bits. So this is the interpretation of those bits in memory, okay? So you also have that available at your disposal when the situation arises, okay? So with that, that's basically what I wanted to cover for type coercion casting in Zig. Once again, being a low-level language, this is a really important aspect when you're dealing with values in memory and having to convert or coerce from one type to another. I hope you find this useful. Do the builder here. I'll see you in the next one.